Hello students, welcome to all fours e-learning session 54. In previous sessions we learned properties of alcohols by breaking by cleavage of CO bonds. In this session we are going to learn same chemical properties of alcohols but dehydration of alcohols. This dehydration of alcohols in previous sessions already we learned, and in methods of preparation of alkenes also we must learn very few reactions. Now we are going to learn much elaborate regarding this dehydration of alcohols. Have a look here. Alcohols which are having CCOH, OH group containing compounds. For dehydration generally acid catalyst we are using, that what we call acid catalyzed dehydration. So when we are using acid catalyst, OH group gets protonate, and after protonation that OH group is going to convert into OH2 plus. Later the CH sigma bond electrons will be shifted, resultant we are getting alkene and water product. If we observe that reaction, it is very clear. There are two products are formed, one is alkene and water, and this reaction is reversible. Forward reaction, backward reaction both takes place. But if you want to get only alkene as product, means forward reaction has to take place more. If you want to get forward reaction more, you have to remove one of the product from the mixer. You have to remove one of the product from the reaction mixer, then forward reaction more takes place. And one more possibility here, you have to heat more. That means by providing more and more heat, so on what basis you can remove? On what basis you can remove one of the product? When you are heating, when you are providing more and more heat, then because of alkenes and water, alcohols, these three are there. Alkenes less volatile, they can readily vaporize out, means they can readily boil, means their boiling point is very less compared to alcohols. So alkenes readily comes out because of hydrogen bonding, because of presence of intermolecular hydrogen bonding. Alcohol's boiling point is high compared to alkenes. So simply in one statement if you want to say, because of difference in boiling point of alkene and alcohol, we can separate alkene easily simply by heating. And one more method is by removing this water. In order to remove that water, we have to use dehydrating agent. That means if you want to see this reaction in forward direction, there are two ways in front of us. One is we have to provide more and more heat. That what we call distillation. During distillation, one of the compound readily boils out. Which one readily boils out here in this mixer? Alkene. Because of no hydrogen bond, alkene's boiling point is less compared to alcohols. In alcohols, intermolecular hydrogen bonding is there. This is clear. And second part, what I said, by using dehydrating agent. What is the role of dehydrating agent? It absorbs. It takes that water. So there are two ways. One is by using dehydrating agent. One is by using dehydrating agent, and another one is simply heat. We have to follow combining of these two. Instead of following only dehydrating agent, or instead of following only just heating, we are going to provide more and more heat. Simultaneously, here we are using dehydrating agent also. Both we are going to maintain. Result and you are getting more alkene. Now, how this reaction proceeds? Let us assume ROH. Here R is not simply methyl or ethyl. One alkyl group, whether it may be primary or secondary or tertiary, don't assume that this one is simply methyl or ethyl. ROH, that is nothing but alcohol. Upon protonation, OH group gets protonate. So whenever OH group gets protonated, it converts into ROH2 plus. ROH2 plus. So protonation of alcohol, that obviously a little bit fast reaction. After protonation, that OH2 plus has to leave. Being OH group, poor leaving group, after protonation it comes to good leaving OH2 plus. So many times we learn. So here this OH2 group is leaving, and ultimately we are getting carbocation. Formation of carbocation is a slow step. Whenever a slow step is there, then obviously we can say rate determining step. That means this mechanism proceeds via formation of carbocation, and wherever carbocation is there, ring expansion rearrangements are there. Keep that point in your mind. And here carbocation formation is the first step. In previous sessions we learned formation of carbocation first step, formation of carbocation slow step, formation of carbocation rate determining step. That is possible in case of either E1 or SN1. So here this is elimination. Hence we can say if alkyl group is able to form stable carbocation, then we can say simply this one proceeds via formation of carbocation. That means that mechanism is called E1 elimination. E1 elimination, and we are getting water. After formation of carbocation, deprotonation, the solvent molecule is going to take that proton and converts into alkene. So if you observe here, formation of alkene, for initially first protonation and OH group converts into OH2 plus, poor leaving OH converts into good leaving OH2 plus. Later in next step, OH2 plus will leave away. After leaving that OH2, water molecule, formation of carbocation takes place. After formation of carbocation, here we are getting alkene by deprotonation. The proton will be accepted by solvent molecule. Now, via mechanism proceeds, reaction mechanism proceeds via formation of carbocation. Mechanism proceeds via formation of carbocation. This reaction is nothing but elimination reaction because of H and OH are eliminating up here, and resultant there will be new pi bond formation in between two carbon atoms. Means by breaking two sigma bonds, one new pi bond formation takes place. This one is elimination, and elimination of two groups or atoms from adjacent carbon atoms. That elimination what we call the beta elimination. In beta elimination we have learned E1, E2 and even CB elimination. Here this elimination particularly belongs to E1 elimination because of via formation of carbocation, and don't forget that alkyl group must have should be either secondary or tertiary. Okay, in such a case carbocation formation is possible. And rate determining step is carbocation formation. Rate determining step is formation of carbocation. That is only slow step here. And here dehydration order of dehydration of alcohols, tertiary greater than, secondary greater than primary. That is nothing but order of stability of carbocations. Tertiary carbocation is more stable than secondary carbocation. Secondary carbocation is more stable than primary carbocation. So here it is nothing but intermediate stability is nothing but dehydration of alcohols because of tertiary is more stable than secondary than primary. Here we are saying that tertiary alcohol is readily undergoes dehydration than secondary than primary. Primary alcohols needs concentrated sulfuric acid and at high temperature 443 Kelvin temperature. And secondary and tertiary alcohols undergoes dehydration even with dilute H2SO4. But primary alcohol requires concentrated sulfuric acid. And for that, what is the reason we will discuss later. Now, as I mentioned that there are two factors which promotes forward reaction or formation of alkene or formation of elimination product. Out of these two conditions, one I said that we need to maintain high temperature. For that, when we are using high temperature, obviously alkenes readily comes out, means readily distills out. And second one, as I mentioned that good dehydrating agent to remove that water. So what dehydrating agents we have to use? There are so many dehydrating agents are there. Let us see a few of compounds from that list. Concentrated sulfuric acid or phosphoric acid. When we are using temperature, we need to maintain 473 Kelvin. Because of we are changing the reagent, temperature obviously has to change. And don't forget that at high temperature, only generally elimination product preferable. Elimination product is always thermodynamic product. Kinetic product here, substitution product. Kinetic product is substitution product means below temperature if it is 40 degrees Celsius. If temperature is below 40 degrees Celsius, then preferably substitution rather than elimination. If temperature we are maintaining greater than 80 degrees Celsius, then obviously elimination product is a major product rather than substitution. So don't forget that elimination that requires more temperature, that what we say here, that is thermodynamic product. Substitution generally fastly happens, that one in general kinetic product. Okay, so we'll discuss regarding the kinetic and the thermodynamic product. Previous sessions already we learned. Okay, and in this session not required, I'm not going to discuss that. Simply I'm focusing on the dehydrating agents, but we should remember one point: which dehydrating agent we are using. Depending upon the dehydrating agent, here different temperatures we need to maintain, and all these dehydrating agents do not follow same mechanism here. And in this session I am going to discuss two dehydrating agents, one which is able to form carbocation intermediate and means via formation of carbocation, and one without formation of any carbocation I am going to discuss. Let us see. H2SO4, H3PO4, 473 Kelvin we need to use, and anhydrous Al2O3 if you are using 623 to 673 Kelvin temperature, and beyond of that potassium hydrogen sulfate also dehydrating agent, and boron trifluoride BF3 and heating anhydrous zinc chloride and heat P2O5 phosphorus pentoxide, phosphoride chloride, POCl3 in presence of pyridine, and dry HCl also good dehydrating agent that already we discussed in previous sessions, and H3PO4, PO3 and 443 Kelvin temperature. Paratoluene sulfonic acid also we can use as a good dehydrating agent. So here we can use any of these dehydrating agent. Ultimately which dehydrating agent we are going to use, that depending upon the given substrate and the remaining conditions or factors. Okay, let us see first here. As I mentioned the mechanism how proceeds. First alcohol group gets protonated. After protonation OH2 plus has to depart via formation of carbocation. After formation of carbocation, then you are getting alkene, means deprotonation takes place, alkene. For that, if you draw energy profile diagram, basically energy of reactants alcohols like this. Alcohols after protonation, for that transit state, this is transit state, and we are getting one intermediate ROH2 plus intermediate, and when OH2 plus will leave away, we are getting carbocation. Formation of carbocation requires very high activation energy. That's why as you mentioned that this is nothing but activation energy for formation of carbocation, and this activation energy is very high compared to any of these steps. Hence we mentioned that this one is a slow step or rate determining step. Formation of carbocation is rate determining step. And after formation of carbocation, we are getting alkene by removal of proton from adjacent carbon. Fine. Here, transit state 1, 2, 3. What number of peaks are there? 3 peaks are there. So 3 peaks and 2 intermediates. One is ROH2 plus, another one is R plus. So always number of peaks minus 1 is number of intermediates. Number of peaks minus 1 is number of intermediates. And here reactants and products. This is energy profile diagram. Regarding this energy profile diagram, previously we learned that in even elimination. And just once again I am going to recall that how we are going to draw, what number of peaks, what number of intermediates we are going to get. Now, I used to consider ethyl alcohol. Ethyl alcohol in presence of anhydrous Al2O3 and 350 degrees Celsius, anhydrous Al2O3 and 260 degrees Celsius. Ethyl alcohol, in both cases, anhydrous Al2O3 only dehydrating agent, but which product we are going to get, that is depending upon temperature what we are maintaining. If it is 260 degrees Celsius temperature, we are getting diethyl ether product, and if we are maintaining 350 degrees Celsius, we are getting alkene as a product. So here, if you observe how it is possible for dehydration, so dehydration takes place here, means dehydration takes place from 2 moles of ethyl alcohol, we are getting ether. And let us see briefly that mechanism, how this reaction proceeds. As we know that anhydrous Al2O3 without any water, obviously it acts as Lewis acid, and let us suppose that C2H5OH is going to combine with anhydrous Al2O3. It forms complex. By donating its electron pair resultant, this oxygen is going to bear positive charge OH Al2O3. Here it gets minus, oxygen gets positive charge. After getting positive charge, this oxygen obviously it pulls the bond pair of electron towards itself, resultant this carbon bears positive charge. Upon that positively charged carbon, second molecule of alcohol has to come and attack. Another ethyl alcohol molecule has to come and attack. Nothing but this is a substitution. Diethyl ether is a substitution product. Diethyl ether is a substitution product, and alkene is elimination product. Substitution here and this one is elimination. Remember that, we will discuss little later regarding this. Which one, in which case substitution takes place and which case elimination takes place. And always elimination, substitution both are in competition. And when we are using anhydrous Al2O3, you have to remember one point here: without formation of any carbocation. There is no formation of carbocation in this mechanism. Reaction proceeds in such a manner. And here are two possibilities, as I mentioned, that one is substitution, another one is elimination. And you notice one more point here: substitution takes place at low temperature and elimination takes place at high temperature. At 260 degrees Celsius, substitution product, as I mentioned, as major product, and at 350 degrees Celsius, I mentioned that elimination product is major product. Okay, remember that point. We will discuss later why we are getting like that. Means with increase in temperature, why we are getting elimination product as a major product. That point already I mentioned in previous sessions in E1, E2 elimination. If you did not remember, once again we are going to discuss that point in 2 minutes. Within 2 minutes. Let us see here the same alcohol I used to consider, and instead of anhydrous Al2O3, concentrated sulfuric acid I am going to use here. When I am going to use concentrated sulfuric acid, first protonation takes place. OH converts into OH2 plus. After leaving this OH2 plus means CH3, CH2, OH2 plus. Then here the proton provided by sulfuric acid H plus and remaining HSO4 minus only acts as nucleophile and it displaces OH2. OH2 means water molecule. Finally, we are getting product C2H5HSO4. This is what we call ethyl hydrogen sulfate. So, ethyl hydrogen sulfate formation takes place at what temperature? 110 degrees Celsius temperature. At 110 degrees Celsius, ethyl hydrogen sulfate. After formation of ethyl hydrogen sulfate, how further reaction proceeds? That depends not only upon temperature but also which one is excess. I mean to say which one is excess. That means alcohol excess or concentrated sulfuric acid excess. Which one is the excess? That we have to consider. Let us see here. After formation of ethyl hydrogen sulfate, if you are heating alone up to 443 Kelvin, if you are heating up to 443 Kelvin alone itself, then this ethyl hydrogen sulfate is going to depart and it converts into diethyl sulfate. So what mechanism takes place here? How diethyl sulfate formation takes place? So because of we are not using either concentrated sulfuric acid excess and we are not using ethyl alcohol excess, neither concentrated sulfuric acid nor ethyl alcohol excess, only ethyl hydrogen sulfate formation takes place. After formation of ethyl hydrogen sulfate, further upon heating it itself alone, then we are getting diethyl sulfate. Diethyl sulfate formation takes place. Diethyl sulfate formation takes place from ethyl hydrogen sulfate by losing water. So, if it heating of ethyl hydrogen sulfate alone, we are getting diethyl sulfate. Keep that point. If we are using ethyl alcohol excess, after formation of ethyl hydrogen sulfate, we can easily displace this OSO3H. We can easily displace OSO3H because of HSO4 minus is a good leaving group. HSO4 minus is good leaving group and its ability to form bond with carbon also very less, and it has, we can say it has more tendency to leave. Then one more ethyl alcohol molecule may come and attack upon this carbon and we are getting diethyl ether. This one happens in presence of excess of ethyl alcohol and temperature we need to maintain 413 Kelvin. So if we maintain temperature, if we maintain more temperature means 140 degrees Celsius temperature. If this one happens at 110 degrees Celsius and after formation of ethyl hydrogen sulfate, where we need to maintain 140 means we have to increase the temperature a little bit and also we have to maintain more ethyl alcohol. In such a case, what happened? Again, substitution. So which one is going to be substituted here? HSO4 minus will be substituted by this C2H5O minus. Means ethyl alcohol, it itself is going to participate in the reaction and H2SO4 comes out, we are getting diethyl ether. And there is one point. So acid catalyzed dehydration, why we need to use only concentrated sulfuric acid? Why we are not supposed to use HBr or HCl? Because of reason is, if we are using HBr or HCl after protonation, counter ion is Br minus Cl minus. That Br minus or Cl minus or I minus, they can act as potent nucleophiles. They may participate in the reaction. But when we are using concentrated sulfuric acid, after protonation, the counterpart what left here is HSO4 minus. That HSO4 minus is not going to remain, means it cannot act as good nucleophile and moreover it has more tendency to leave. That means it facilitates more for substitution or elimination. That's why acid catalyzed dehydration always we prefer to use concentrated sulfuric acid. So two cases completed. First one after formation of ethyl hydrogen sulfate. If you heat alone that ethyl hydrogen sulfate up to 443 Kelvin, then we are getting diethyl sulfate. And next case I mentioned that in presence of excess of ethyl alcohol, when we are heating up to 140 degrees Celsius or 413 Kelvin, we are getting diethyl ether. Now case 3, in this case we are going to heat this ethyl hydrogen sulfate, form ethyl hydrogen sulfate in presence of excess of concentrated sulfuric acid and 443 Kelvin. So 443 Kelvin is high temperature. This one is 443, this one is 413, 443. Difference in between these two reactions in absence of any reagent here. No one is excess here and here excess is concentrated sulfuric acid. So when concentrated sulfuric acid excess we are using, because of high temperature here what happened? Ethylene takes place. Ethylene formation takes place. So first ethyl hydrogen sulfate formation. After that how reaction proceeds, that depends upon which one is excess and what temperature you are maintaining. If nothing is excess, one case. If ethyl alcohol is excess, substitution, and if concentrated sulfuric acid is excess, then we are getting elimination. Sir, okay, ethyl alcohol you consider like this. If we consider methyl alcohol, can we expect the same reaction? Yes, obviously. So here dimethyl sulfate you are going to get no doubt in that one, and dimethyl ether you are going to get no doubt in that one. But methylene formation do not possible. That's why this reaction means with concentrated sulfuric acid, CH2 formation do not takes place, except that remaining two reactions are same with methane. Now, if you observe here in between these two difference, anhydrous Al2O3, whenever we are using anhydrous Al2O3, what happened? We are getting the same substitution ether and alkene elimination product. Substitution product and elimination product. So substitution is ether and elimination is alkene. That two are possible. And with concentrated sulfuric acid also, that two are possible. But the difference in between these two, whenever we are using anhydrous Al2O3 or little pyridine, anhydrous Al2O3 and a little pyridine, which suppress formation of carbocation, So the suppressed formation of carbocation, it means that there is no more formation of carbocation in presence of Al2O3 and a little amount of pyridine. In such a case, there is no possibility for formation of carbocation. So whenever there is no formation of carbocation, obviously there is no rearrangement and ring expansions. That means with anhydrous Al2O3, always you are getting one product, means without formation of carbocation. Whereas with concentrated sulfuric acid mechanism, preferably via formation of carbocation. Don't think that with ethyl alcohol, okay? Ethyl alcohol is primary alcohol, primary carbocation is not possible. So with not with ethyl alcohol, if alcohol is secondary or tertiary alcohol, in such a case what happened? Via formation of carbocation. Via formation of carbocation means rearrangements are possible. That means you may get a mixture of products. But anhydrous Al2O3 not like that. So if you observe here, because of elimination, we already learned two things. One is stage of elimination or Zaitsev elimination, and the second one is Hoffman elimination. So which elimination is major? Obviously, from first onwards we are learning that Zaitsev elimination is a more substituted alkene as a major product, and Hoffman elimination is only less substituted alkene is a major product. But Hoffman elimination, we already learned that in few cases only, like if the leaving group is poor leaving group, if the attacking base is bulky base, in such cases only we notice that Hoffman elimination. Here regular elimination, that is Zaitsev elimination or Zaitsev elimination. Let us see. I used to consider 2-butanol. 2-butanol upon dehydration by using concentrated sulfuric acid, we are getting two products. One is 2-butene, another one is 1-butene. In case of 2-butene, both are double bonded carbon atoms attached to methyl groups, that means disubstituted alkene we can say. In case of 1-butene, it is a monosubstituted alkene. So this 1-butene we can say Hoffman product, and 2-butene we can say Zaitsev product or stage of product. Experimental evidence, 80% of 2-butene we are going to get, and 20% of 1-butene we are expecting if elimination only takes place. If you provided conditions only for elimination, means if you are expecting 100% elimination product, then in such a case 80% is only Zaitsev or stage of elimination and 20% is Hoffman elimination. So elimination here proceeds via formation of carbocation with concentrated sulfuric acid, no doubt in that one, with anhydrous Al2O3 and little amount of pyridine. What happened? Here isomerization prevented. That means we can use a different terminology. Like earlier I mentioned that without formation of any carbocation, rearrangement and ring expansions are not possible. So hope that frequently I am using that sentence, you may get boring, little bit boring, right? So now change the terminology. So what do you say here? Isomerization will be prevented. Means isomerization prevented means what happened? By rearrangement only you are getting different isomers, right? Isomerization prevented by using anhydrous Al2O3, whereas in case of sulfuric acid, isomerization we cannot prevent. So isomerization prevented there by using anhydrous Al2O3 as dehydrating agent, along with that a small amount of pyridine also. And here you should remember, primary alcohol not possible to form stable carbocation. Example ethyl alcohol. Generally secondary and tertiary alcohols, they are able to form secondary carbocation and tertiary carbocation. That means secondary and tertiary alcohols are able to form stable carbocations. In such a case even elimination is possible. Whereas primary alcohols also can proceed even elimination. Condition is if a beta carbon must and should be either tertiary or quaternary. Beta carbon is must and should be either tertiary or quaternary. Beta carbon is a tertiary or quaternary. What do you mean that, sir? So assume that this OH containing carbon alpha and next carbon is beta. So beta carbon must and should possess at least 2 or 3 alkyl groups. In such a case, tertiary or quaternary. So if beta carbon is more bulky with alkyl groups or electron releasing groups, with bulky groups like alkyl groups or electron releasing groups, in such a case, even though alcohol is primary alcohol, by providing a little amount of heat energy, it is able to form stable carbocation. And after formation of carbocation, what happened? Because of migration of alkyl groups takes place. That I'll explain in examples. Migration of alkyl group takes place, and because of migration of alkyl group, what happened here? You are getting again isomerization takes place. Means you are getting isomeric products and you are getting mixture of products, we can say. So generally secondary and tertiary alcohols proceeds via even elimination, and primary alcohols can also proceed via even elimination and condition is beta carbon must and should be either tertiary or quaternary. And if primary alcohol is there in which beta carbon is either primary or secondary, beta carbon is either primary or secondary, that means that this beta carbon do not attach to any alkyl group. All are hydrogens or one hydrogen. All are hydrogens or one alkyl group. Presence of all are hydrogens or one alkyl group. In such a case, what happened? Here, it do not form any stable carbocation. Without formation of any carbocation, then product, what you can say? Here, you are getting elimination product, but not via formation of carbocation. Without formation of carbocation, then what you want to say? Obviously, E2 elimination is more famous. E1 elimination and E2 elimination. So, hope you got this box. Gives complete information to you. Secondary and tertiary gives C1. Primary alcohol with beta carbon more hindered means tertiary and quaternary. But remember that hindered means not with electron withdrawing groups. If electron withdrawing groups are there, they do not facilitate to form carbocation. That must be that alkyl group, that groups must be either alkyl groups or strong electron releasing groups, but there should not be any electron withdrawing groups. In such a case, we are getting E1. And if beta carbon is attached to only one alkyl group or no alkyl group, in such a case, no doubt it is. This one follows E2 elimination. And don't forget that E2 elimination again proceeds without formation of carbocation and anti-periplanar elimination. E2 elimination is anti-periplanar elimination. Now, let us see how in substitution and elimination, how temperature predominates elimination. How temperature predominates elimination. That we will discuss in the next session.